You all for being here. It's exciting to get to talk to such a big community of plant conservation and ecologists. So I'm going to kind of take us away from Rumble, just a couple of hours north to a field station closer to Boulder. And we'll be talking again about shifting phenology, so a lot of the same themes. So shifting phenology is the timing of these life history events, and it's one of the most common responses to environmental change that we see across a whole bunch of taxa. So some of these patterns include things like shifting migrations earlier in the year for birds, and then this advanced and compressed breeding seasons and a whole variety of different organisms. So birds, mammals, insects, amphibians, and then plants. And so for plants, the timing of these life history events include germination, leaf out, flowering, and fruiting. And as we've heard, the timing of each of those transitions is really sensitive to these local environmental conditions like temperature or precipitation. And so climate change may be causing this mismatch between the conditions that historically cued a plant that it was a good time to start growing or reproducing versus the conditions that they're experiencing even now and then certainly into the future. And so generally, we know that phenology is advancing over time, and that correlates with warmer climates. So this meta-analysis is showing spring phenological events in Europe, and most species are advancing their phenology over time in these red bars, but there are a handful that either don't advance at all, so these guys near zero, or delay their phenology in blue. So it's advancing, but pretty variable patterns under changing conditions. And this can have a whole variety of different consequences. So it can determine exposure to environmental conditions. So for example, as we just heard, if you flower too early, you might get hit by these late frost events. So this is showing complete abortion of flowers in Michigan blueberry crops about a decade ago. But on the reverse end of that, if you flower too late, you're going to get hit by these late summer droughts, especially in these dry or alpine areas. It affects resources to access to resources like space, water, and light, affects plant pollinator interactions and competition with other species in the community. And so altogether, shifting phenology is likely to affect fitness and population dynamics, but these effects can vary across multiple scales, ranging from variation at the individual level and then scaling up to affect populations and even communities. So studies that are asking whether phenology is shifting under forecasted relative to historical climates typically look at whether the population mean, shown with this black bar here, is showing that advance in phenology. But this approach assumes that every single individual within the population, so each of these gray lines in this figure, are advancing phenology to about the same degree and in the same direction as this overall population mean. But individuals can actually vary quite a bit in their responsiveness to climate, and this is called individual by environment interactions. But in this scenario, we might have some individuals that do shift their phenology substantially in response to warming conditions, some that don't shift very much, so these less steep slopes near the top. And then we might even have a handful of individuals that delay their flowering, so in the opposite direction of the population average. And this pattern can result in different amounts of variation in phenology, where under historical climates, most individuals are flowering really synchronously. Everything's happening kind of at the same time. Whereas under a forecasted climate, we get this wider spread in the timing of these phenological events. But we have pretty limited evidence for I/E in natural populations, especially in plants, simply because it's pretty data intensive. So you need to track the same tagged individuals over many years. So during my postdoc and continuing on with work in my lab, we've been monitoring phenology on individuals of Silene acaulis, which is an alpine cushion plant. in this long-term observational study conducted at the Niwot Ridge LTER in Colorado. And so for 6 years, we've been collecting data on flowering time, as well as a bunch of different vital rates, including survival, size, and fruit production. And we've compiled a bunch of climate data, including temperature, growing degree days, which is a measure of heat accumulation, and snowmelt timing. And so in this system, we know that flowering time advances nonlinear with warming. So this is showing you first flower as Julian day of year in response to seasonal GDD. And so for GDD, just warmer or higher values of GDD, so more heat accumulated means warmer conditions. And so flowering is earlier with more GDD. And then really similarly with snowmelt, we see that flowering time is earlier when snowmelt is earlier in the year. So we're thinking about I/E in this system because Silene is a really long-lived perennial. And so it's not likely to evolve quickly in response to climate change. And so plasticity is likely to be this really key determinant of whether it will persist. And so for this first section, I'm going to just ask, do individuals vary in their phenological responses? Do we see I/E at all? And then how does the variance in phenology shift with warming? So this figure is showing you individual reaction norms for every plant's response. So first flowering response to GDD. So each line here is an individual plant in the study. And so here, what I want you to just note is that the majority of individuals are advancing their flowering under warmer conditions. So, but there is a lot of variation in those responses, with some individuals shifting really dramatically, some not responding much at all, and then some actually delaying. And then we see similar patterns for snowmelt. So again, flowering is earlier with earlier snowmelt, but there's a lot of variation in the magnitude of these species responses. So then when we estimated the variance among the individuals in those data first flowers, we saw that variance is increasing as conditions get warmer and is higher when snowmelt is warmer. So that matches our predictions about this increase in variability in phenology under forecasted conditions. So for this section here, we see that individuals do advance flowering, but to pretty different degrees. So some evidence for I/E. And that seems to be resulting in this increase in individual variance under warming conditions. And so some of our next steps here is we're interested in scaling up from thinking about individual variation to how that affects population level variation. This increase in variability in phenology can cause a lot of mismatches with co-flowering, conspecifics and heterospecifics, alter floral displays, and affect pollination. So we'll start teasing out some of those consequences. And then finally, because we have all of these reaction norms for actual measures of individual level plasticity, essentially, we're starting analyses trying to actually test for selection on plasticity itself. So that hopefully will be coming in the next year or so. Okay, so these individual level responses can then scale up to affect population dynamics. And so I'm showing you a scenario for shifting phenology, again, under forecasted versus historical climates, under 3 population growth scenarios. And so when populations are declining, we might expect that they're not shifting their phenology in response to climate much at all. In a stable population, we might expect that phenology is shifting just enough to track suitable conditions in time. And then in an expanding population, we might expect to see this greater responsiveness or this steeper slope for phenology's response to climate. And these 3 scenarios can translate to changes in population growth rates lambda. So here I'm mapping these three scenarios onto values of lambda, where light values indicate a declining population, less than 1. Orange is going to be our stable population at replacement, so lambda of 1, and then red will be our expanding populations where lambda is higher than 1. And so here in this declining population that doesn't manage to shift its phenology, we would expect to see this decrease in population growth rates or different measures of fitness under these forecasted climates. In a stable population, we might expect that the phenology is shifting to track suitable conditions, and so populations remain stable. And then in an expanding population, we would expect to see that there's some advantage to this greater responsiveness to climate that, at least to some extent, allows population growth rates to increase to be greater than 1 and allows the population to grow. So still working with Silene, I'm going to address whether phenology is under selection, and then whether plasticity and phenology appears to be adaptive in this system. And so to do this, we tested for selection on a couple of measures of climate-driven phenology. So we correlated fruit production using this as a proxy for fitness with 2 climate-relevant measures of phenology: the number of GDD you accumulate by the time that you produce your first flower, and then the number of days between snowmelt occurring and your first flower. And so in these figures, lower values in both cases indicate flowering under colder conditions. And that can happen in 2 different ways. So it can happen because you flowered earlier in the season, so with fewer GDD accumulated, or very rapidly following snowmelt, or it could just be a really cold year. And then on the other end of that spectrum, high values indicate flowering under warm conditions, so later flowering later in the summer or just in a warm year. And so this analysis can't tease out those 2 mechanisms. But what we found was that fruit production is much higher at low values of both heat accumulation or GDD at first flower and days between snowmelt and first flower. And so there's directional selection for earlier flowering under these colder conditions, regardless of how that occurs. So we did then try to tease out this relationship using these non-parametric fitness landscapes. So here I'm going to be showing you the relationship between climate. I'm only going to be showing you GDD here, first flowering time, and fruit production. And you can picture this as these dark red isoclines here are our fitness peaks. And then we move kind of down into the valley where there's lower fitness in the dark blue. And so here we find that reproductive success or fruit production is highest when GDD is lower. And it's also highest under these kind of early to intermediate flowering times. And so since we know in this system that flowering is shifting to be under those colder environmental conditions or earlier in the season, that does appear to track this fitness or this phenotypic optimum to be flowering under cold. But the caveat to this is that even when you flower really early, when temperatures or GDD is really high, populations are falling into fitness is declining incredibly rapidly. So this means that even though plasticity appears to be adaptive in the system, it's not likely to be enough as climates continue to warm. And as if you track individual populations through time, so these larger symbols are our population means by year. If you track them through time, you see that the populations are falling from these higher fitness isoclines into these lower ones. So for this section, we do see directional selection for flowering under cold conditions. So whether that's earlier flowering or flowering in a cold year. And plasticity seems to be tracking this optimum of cold, but it might not be sufficient to maintain fitness as temperatures get warmer and warmer up in this corner of this graph. And so to wrap up, phenological shifts are in the direction favored by selection, but that appears to be insufficient to maintain fitness under rapid warming, and these are even conditions that we already see in the field. But there's a lot of individual variation in phenology, and that has unknown consequences that we're just starting to think about for pollination and population dynamics. But right now, we're seeing that the negative effects of climate change might really outpace any potential benefits of phenological shifts in this system. So with that, I'd like to acknowledge that our work is conducted on the lands of the Cheyenne people. Thank a whole lot of people who helped with field collection. And I maybe address questions, but maybe in 10 minutes. So thank you.